In the last session, we started talking about principal components analysis, how it works, and how we can use it to investigate relationships between measurements. In particular, we looked at an example of our undergraduate business programs and trying to find principal components to represent the measurements that we had for program quality, student quality, and placement. We talked about using PCA for identifying relationships between the columns, and the key there is to look at the weights that you get for each one of the PCs. Larger weights tell you that that original variable contributes more to the PC, and large can be positive or negative. We're now going to look at PCA used for dimension reduction, for reducing the number of columns. And this is very useful in predictive modeling, where we really want to deal with fewer predictors for lots of different good reasons. We'll also look at the use of PCA for actually being able to look at our records on a 2D chart rather than this multidimensional view which we have due to the many measurements. So how do we reduce the data dimension? Remember that we get PCs, we have the same number of PCs as the number of the original measurements. However, the information is divided differently in the PCs. It's divided in a fashion so that the first PCs contain the most information in a graduating way, and that each one of the PCs is uncorrelated with other PCs, so there's no information overlap. In our example, we saw that PC1 captured almost 77% of the total information that is conveyed by the entire set of 6 measures. Take a look at the output that we had and see how many the first 2 PCs capture. You'll notice that they capture around 90% of the information. This means that if we only take the first 2 PCs and drop the next 4 PCs out of the analysis altogether, we only lose 10% of the total information that was contained in all 6 measurements. This is what we call dimension reduction. Now, to do dimension reduction, we have to think, what does it mean to keep 2 PCs? What are these 2 new columns that we have? These 2 new columns are going to be principal scores. To compute a score, we're again simply taking a weighted average of the original measurements. For example, if we take Brown University, and I'm going to use the normalized numbers that we obtained earlier on, I'm going to take each one of the weights that we had in the PC1 column and multiply it with each of the measurements for Brown University. The first 2 numbers are multiplying the weight for SAT with the normalized SAT. And we do this for all of our 6 measurements to get a PC score of 0.989. This is the PC1 score for Brown University. Similarly, we can compute a PC2 score. The only difference will be that we're going to be using a different set of weights. And we can have 6 PC scores for Brown University. In other words, we can replace the original 6 measurements with 6 PC numbers. Of course, we don't really want to keep all those 6 numbers. We're only going to use the first 2, the PC1 score and the PC2 score. Here are the scores computed for each and every one of the universities for PC1, that's this column, and for PC2. So now for each university, we have only 2 numbers. Remember that these PC scores are uncorrelated, and therefore, if we take a correlation between these 2 columns, you'll find that the correlation is approximately 0. That's how we use PCA for data reduction. Now we'll look at how we use this reduction as another step into looking at our data in a 2D visualization. When we only have 2 P's that capture most of the information, that's relatively simple. All we're going to do is plot a scatter plot of the scores on PC1 versus the scores of PC2. Remember that these 2 sets of PC scores represent the multivariate relationship between the original 6 variables that we had earlier on. Sometimes you'll need more than 2 PCs to capture sufficient information, and then you might need 3. Then you'll need a 3D plot, or else you'll have to look at pairwise charts. But looking at the first 2 PC charts is always quite interesting, and sometimes it will reveal some patterns that you didn't think about before. Let's look at what we have right now. Here are all our universities on a scatter plot of PC1 versus PC2. And we can see, interestingly, different clusters of universities. We can see that some universities have high PC1 scores, but relatively low PC2 scores. We also have universities that have high PC2 scores and high PC1 scores. Now, if we were able to assign a name to these PCs or capture what they were actually measuring, then this would also be easier to interpret. But again, we get an idea of which universities are similar to others or different from others. I'm going to take you one step further and just mention singular value decomposition. Sometimes people use PCA or SVD interchangeably. And what SVD is it's basically a type of PCA. It's actually a generalization of PCA and is a much faster and computationally efficient method to do dimension reduction. If you've heard of the Netflix prize, SVD turned out to be one of the major tools early on in this competition. In this competition, we had a huge matrix of users rating movies. So we had records being users, and we had movies perhaps being columns, and we had a very, very sparse matrix, meaning that we had many cells that were empty because many users did not rate many movies. SVD was a very useful approach to reducing the dimension of this huge and very sparse matrix. So you might see SVD being used in large data mining tasks. Here are some points for thought and discussion on the forum. Well, if we're going to use a subset of these principal components, say only the first two, is this going to be useful in a predictive context? Is it going to be useful in an explanatory context? Remember, we're reducing the dimension maybe only of the x's. Do we want to include a y in there as well? These are all questions that you should ponder and think how that would be useful to use PCA. Another question and point for thought is, remember we talked about stepwise methods or even domain methods to just removing some of the variables a priori and sticking with just a subset of the original measurements. What are the advantages of using PCA over that approach? What are the disadvantages of using PCA over that approach? These are some good points to think about and consider, and please discuss them on the forum as well.